I'm here to talk about how Anthropic uses GKE to run inference for Claude. We're going to have a couple of presenters today. I'm Nova. I'm a member of technical staff at Anthropic. I've been there since about October 2021, which is a long time for us. And I'm joined by Nathan and Ning from GKE, who will be taking the second two parts of this presentation here. Here's your agenda for this evening. I'll be talking about how we serve Claude, what it says on the tin, and then Nathan will be talking about large-scale, cost-effective inference, so you guys can learn some of those same lessons. And then Ning will close us out with talking about serving Gemma, exciting new model out of Google. So let's talk a little bit about how we serve Claude. So a little bit of background. Tease you there. Anthropic is an AI safety and research company founded 2021, building reliable, interpretable, and steerable AI systems. So we're building safe AI that help you get your work done. And we develop large language models like the Claude 3 family, now available on Vertex. Opus is coming very soon this week on Vertex. And yeah, our mission is to ensure that AI helps people and society flourish by building frontier systems, studying their behaviors, working to responsibly deploy them, and regularly sharing our safety insights, but you could see that on the slide. Let's talk a little bit about Claude here. We built the Claude model family to offer the best set of models across intelligence and speed requirements, all at a lower cost than comparable models. You can look at that GPQA score there. That's my favorite one of our evals. So you can see the graduate level reasoning there. We're doing pretty good on that one. Opus is our most powerful model. It's the most intelligent model available on the market today. Achieves state-of-the-art intelligence superior to GPT-4T. Sonnet strikes a balance between intelligence and speed and is priced to be significantly cheaper while achieving comparable levels of intelligence. And everyone seems to really like Haiku. It's very, very fast for quite a lot of smarts there. So, and it's image-to-text vision, which is pretty exciting for a lot of new use cases. But let's talk a little bit about how we actually do this. You didn't come here for the marketing. So one of the things that we run into when we're doing ML ops at scale, which is a lot of buzzwords there, is these reliability challenges for individual servers. So you've got a lot of GPUs, you've got a lot of TPUs. Together, you've got a lot of problems. And when you've got that many servers, you have to do a lot of maintenance. Google helps us with this today through a bunch of different things. But one of the things I want to talk about is customer-triggered maintenance, which lets us have control over the times that we take maintenance, which means that we're able to run closer to 100%, which we really need with Claude right now, and limit the amount of downtime that we have that's unexpected, which is pretty exciting. GKE makes it easy to automatically drain nodes when we receive a maintenance request, while still having a graceful period for terminating our workloads. Like I said, we're using Kubernetes. We want to be able to use those features there. This respects things like pod disruption budgets, which is pretty useful when you have large-scale workloads spanning multiple nodes. I've got this fun slide here. You'll see another version of this slide later in the presentation, but we serve Claude through stateful sets. No fancy CRDs at the moment. And we have multiple of those inside of the same GKE cluster. And this is just sort of a visualization of the sorts of things that we're using out of Kube today. And I want to talk quick shout out to a project from Abdullah at GKE, Leader Worker Set. This is something that you can find online. It's now in Kube SIGs here. This is super helpful when you're serving a workload that might have two different kinds of resources under it. So you might have some kind of like load balancer or a queuing server, and then you have a bunch of very, very expensive TPUs or GPUs. You don't want to dedicate one of those to serving that queue, and Leader Worker Set lets you have one leader for all the stateful set, one leader and then a stateful set that's following that. And let's talk about Kube for Claude. Obviously, Kube provides a lot of benefits across a lot of different kinds of applications, but for something like Claude, one of the challenges here is like service discovery, and obviously Kube gives us like a very clear answer for that. we've got this other fun part of this diagram here pointing at. We're also using Cloud Run. I'm sure someone will talk about that one day. Optimizing utilization is easier with pods as an abstraction. We have multiple replicas of the model. We want it to be able to be scheduled across some large fleet of nodes. There's no better way to do that today than using containers and Kubernetes. And I want to point at one other, this is another Abdullah special here, is the pod scheduling readiness feature, which went into alpha in 1.2.6 and is beta in 1.2.7. I think it's going to hit stable in 1.30, but why wait? So much stuff is in beta in Kube. But one of the things that it lets you do is have control over the scheduling of your nodes or of your pods and your workloads without having to replace the entire scheduler. This is really convenient if you have things like topologies that you want to enforce without having, again, running your own scheduler. You're using GKE, not running your own cube. And we're also in this multi-accelerator world. I've talked about GPUs and TPUs. I'm going to talk a lot more about TPUs in a second. But they are easier to interchange when your workloads are running on Kube because you don't have to manage the individual node fleet and tie the drivers and things like that together. You can deploy those automatically through GKE. And so if you haven't seen one, this is a TPU. This is actually, sorry, this is 4 TPUs across 2 VMs with 2 chips each, but who's counting? Each of these chips computes 393 teraops per second, which is like a pretty exciting number, but it also doesn't mean anything. So let's like make a, let's put this together for a second. Imagine doing a multiplication in your head, just do, 2 times 15 here. Do 100 of these a second for 125,000 years. I'll wait. Okay. Well, now you've caught up with what one of these chips does in a second, and we use 256 of them together in a toroidal high-speed mesh, which is a lot of numbers. We do use fewer of them for some models. TPUs let you slice things nice. And here's a figure that I've taken from Google that shows how those are connected. You can see there's this mesh here, and you can see the wraparound links that let you have high-speed ring communications. If you're doing ring ops, TPUs are really great for that. And we leverage TPUs inside of GKE rather than running Cloud TPU outside of it. We find that they work quite well together and deliver high throughput for our inference workloads, which is faster response times, more efficient resource utilization, and the orchestration gets a lot easier with Kube. And ICI provides a performance boost for our TPUs. ICI here being the interchip interconnect. It's a high-speed optical interchip interconnect, if you're counting. And having JAX is great because it means that when you have a research model and you want to bring it to prod, you can just sort of scale it up. It just works, which is amazing and is not something that I find with PyTorch. So, and yeah, cost-effective, scalable, GKE plus TPU. I think I'm running low on time here, so I'm going to talk a little bit about this and then hand it off. But this is the way that TPU and GKE work together. You get this abstraction of a node pool, and that node pool corresponds to a single slice. This means that when you're scheduling your workloads, you can take the easy way out and do a interpod affinity based on node pool. That's maybe pretty specific here, but I think it's pretty useful. And the scheduler takes care of all of that for you here. So everyone loves a quote. Tristan's our performance lead at Anthropic, and he finds TPU optimization even more fun than GPU optimization. The architecture is simpler and more like a puzzle than a mystery box. I think that's basically true. I think a systolic array is a much more elegant design in a lot of ways than what we get out of GPUs. And finally, its orchestration, you want to put it in Terraform. GKE has good support for the kinds of Terraform things that you want to do. We use Terraform for managing our GKE clusters, and it pretty much works. GKE gets our TPUs and GPUs serving customers faster. The resiliency, the fault tolerance, being able to have workloads that are using 100% of your nodes faster without as much holdback means that we can actually serve our customers. Now, we're still running into issues with capacity. Don't get me wrong. I'm sorry about the rate limits, but it's still something that we're doing better on GKE than we would be if we were building all of this ourselves. And with that, I'm going to hand this off to Nathan to talk a little bit about how you can do some of your own large-scale, cost-effective inference on GKE. And I'll be back at the end for questions.
Great, so Nova was able to speak about Anthropic's experience, and I'm sure all of you are here as well because many of you are yourselves interested in serving using GKE, serving using TPUs or GPUs. So I'm going to help you do that in a way that is cost efficient at large scale. To do this, we're going to start at the bottom of the stack and talk about how at every layer of the stack, Google Cloud helps you to serve cost effectively and efficiently using GKE and all the way up the stack. So let's start at the bottom of the stack, talk about cost-efficient inference. TPU v5e is the latest generation of our cloud TPU accelerators. So we started designing our own TPUs back in 2017, made those available. V5 is the latest generation, comes in two variants, v5e, v5p. V5e variant, the E stands for efficient, super efficient, fantastic price performance for inference workloads. We find up to about 2.7x higher inference performance per dollar than TPU v4. Fantastic offering. TPU v5e is also incredibly fast, so you get fantastic latency, very good response, fast serving, and super scalable. So Nova spoke earlier about you can slice the TPU v5e, lots of flexibility in how large you provision. And what that means is that the size of your TPU v5e can perfectly match the model size that you have. So you're not wasting by over-provisioning a much larger AI accelerator than what you actually need. So fantastic, cost-effective way to serve using GKE. Customers like Assembly AI have found Cloud TPU v5e consistently delivered up to 4x performance per dollar compared to other solutions that were available in the market for running inference on their production ASR model. So fantastic results from other customers, and I think your experience on TPU v5e will be fantastic as well. We also offer NVIDIA's latest inference-optimized GPU, the NVIDIA L4 GPU. That's part of our G2 VMs. Super fast, so 4x better performance than the T4 previous generation. Super affordable. In our studies, we found about 40% infrastructure cost savings relative to other GPUs that are on the market, like the A10G, and a global footprint to allow you to position GPUs super close to your end customers, get very low latency round-trip serving. So great TPU offering, GPU offering, and customers like AppLoving have found that they're able to achieve nearly 2x improved price performance compared with industry alternatives by using the G2 VM and the L4 GPU. So fantastic offering for low latency, cost-effective, GPU-based inference. Now, when you're serving a model, you have to think about right-sizing your GPU or right-sizing your TPU. And so we've done a lot of benchmarking here to try to save you the time so that you don't have to do the benchmarking. You can just get a good out-of-the-box recommendation here that's going to help you find the right GPU. What we find with Llama 2 7B, so the smaller Llama 2 model, you can fit that on a single L4 GPU. And at larger batch sizes, that's going to provide you better throughput per dollar than A100 40 gigabyte. Flip that around, and if you're serving, say, a larger Llama 2 model, 70 billion parameter model, then as you get to larger batch sizes, the A100 40 gigabyte GPU is going to give you better price perf there. And that's because you're going to spread that model across multiple L4 GPUs. You get fantastic price perf in that way. So the wide array of GPU offerings that Google Cloud has allow you to perfectly match the model that you're serving to the underlying infrastructure that we have here. So choose L4 if you've got a small model, choose A100 or H100 for larger models. So I want to move up the stack and talk about how at the Kubernetes layer, we have a wide array of tools that help you cost effectively serve at very large scale. So one, we offer container preloading for super fast startups. So let me explain the problem that we're solving here and how this is a real game changer. I'm super excited about this. So when you're serving models, you have to over-provision for the demand that you currently have today. And the reason why is because that demand from your customers varies over time and varies in a way that's unpredictable. And so as demand rises, if you were perfectly provisioned for exactly today's demand, as demand rises, you need to spin up some new VMs, get your container scheduled and unpacked and running on those VMs, and that all takes time. And the time that that takes is time in which you are essentially under-provisioned for the sudden spike in demand that occurred. So you've got to over-provision in order to handle that, and that over-provisioning costs money. So what we've done is we've made it possible to preload a container image onto a secondary boot disk. This means after the node is spun up, Kubernetes schedules the container on that particular node, and rather than taking a long time to fetch the container over the network, because oftentimes inference container images can be very, very large. I've run into customers with many, many tens of gigabytes for a single container image. Not at all uncommon when you're serving large models. That network time is slow. So what we've done is we've replaced slow network fetch time with fast read from a secondary boot disk time. So Vertex AI's prediction endpoint, which is built on top of GKE, they found with their 16 gigabyte container images, they found a 29x improvement in container startup time by switching over to using container preloading with a secondary boot disk. 29x is the type of game-changing improvement that can really allow you to substantially reduce the amount by which you need to over-provision and still be super responsive in spinning up as demand rises. And all that means for you is you save a lot of money. But there's more. So not only can you preload container images, you can also preload any arbitrary data, like model weights. So if you additionally need to fetch large amounts of model weights or other data, you can preload that too. So tell Kubernetes, here's where that data lives. We will preload it, store it on a secondary boot disk, and then once again, you replace slow network fetch time with fast read from a secondary boot disk time. So save a lot of money in that way as well. Additionally, we offer Cloud Storage Fuse. So this became generally available in August of last year. Cloud Storage Fuse has a bunch of benefits around compatibility, Python native file semantics, and other things. But for the purposes of cost-effective inference, I'll highlight one particular benefit here, which is much faster fetching of data from Google Cloud Storage. So customers have found substantially faster loading time when loading a model from cloud storage, thanks to Cloud Storage Fuse. And you get the benefit as well of portability. So substantial portability across clouds. You don't have to learn GCS file semantics. You just use Python native file APIs, and that allows you to read the data that's stored in cloud storage. And you read it a whole lot faster, which just translates to saved money. So OpenX, for example, they found with Cloud Storage Fuse resulted in about a 40% improvement in pod startup time. So back to what I was talking about earlier, faster pod startup time is just saved money for you because you don't have to over-provision anywhere near as much. GPU time sharing, another fantastic way to save a lot of money. So for certain types of workloads, for example, if you've got notebooks, you've got maybe lower demand inference workloads, so you're serving a model, but that demand kind of falls fairly low during certain times of the day, maybe overnight. You're not fully utilizing your GPU. Traditionally, Kubernetes has one container per GPU. With GPU time sharing, you can get lots of containers all sharing a single GPU in a way that helps you to boost GPU utilization, save a lot of money in that way. So Scene has found that GPU time sharing between their pods has increased their average GPU utilization about 1.6x, helped them lower their costs about 66%. So substantial money saver for them, improving throughput, improving utilization for their GPUs. We just released few days ago, NVIDIA multi-process service. So this is now generally available. Fantastic offering that provides somewhat similar functionality to time sharing, but without some of the downsides that time sharing includes. So NVIDIA multi-process service, huge improvement in your ability to have multiple containers running on a single GPU. We also added support for GPUs and TPUs in GKE Autopilot. So with Autopilot, that's our fully managed mode of operation for Kubernetes. So it gives you a serverless-like Kubernetes experience. All GPUs, TPUs available there that allow you to therefore focus on the things that matter to your business and not need to deal with managing infrastructure, deal with spinning up nodes, tearing them down. Autopilot allows you to save a lot of your own developer time and lift that burden off of your team, give Google that burden. And we've got an SLA backed by Google SREs and SLA attached at the pod level for your particular pods running on Autopilot. So it gives you a whole new level of automation within your infrastructure. Contextual AI has found that with GKE Autopilot, they can very easily scale pods, optimize resource utilization, ensure security and availability of their pods, and they've found Autopilot to just be a really great offering for them. Now I'm going to welcome Ning up, who's going to share about Google's latest model, Gemma.
Hello, everybody. I'm Ning. I'm an Eng lead in GKE. My team have been working with Lova and her team in Anthropic to support Anthropic to onboard to GKE and GCP last year. As you can see, Kubernetes is such a powerful and open container orchestration platform. Google Kubernetes Engine, GKE, as the first managed Kubernetes service in cloud, is still the most scalable leading Kubernetes service in the market today. GKE provides flexibility, performance, efficiency for you to deploy your production-ready multi-cloud AI inference solutions. GKE allows you to pick your choice of framework and optimize the inference stack and orchestrate your AI model serving at massive scale across specialized compute, GPUs and TPUs. With this flexibility and the advanced product capabilities that Nathan just showed in GKE, a wide range of models can be served effectively and at scale in GKE. Lova just showed how GKE serves Anthropic's Claude. In the next few minutes, I'm going to give a quick overview on how GKE serves Google's own open source model, Gemma. So you must have heard a lot about Gemini these few days. Gemma is a family of lightweight, state-of-the-art open models, open source by Google. It was created with the same research and technologies that is used to create a Gemini. There are multiple ways to integrate Gemma to GKE. Google has built a partnership with Hugging Face. Gemma is available on Hugging Face. The Gemma model card on Hugging Face will bring you to Vertex Model Garden. From there, you can deploy Gemma to Vertex AI, which runs on top of GKE, or to GKE directly. You can also play it with Google Colab Enterprise Notebook. Kaggle is another option. Some of you must have visited the Kaggle booth here. So we have published a detailed step-by-step guidance for you to deploy Gemma on GKE on GPUs using Hugging Face TGI, VLM, or NVIDIA's TensorRT LM. A few weeks ago, NVIDIA in their GTC announced LIM, NIMO Inference microservices. So in short, NIM is an opinionated, optimized microservices framework on top of TensorRT and ALM for a selected set of models. So we are working with NVIDIA to make Gemma as part of that stack. This morning, there was a session. Hope some of you already attended it. Yeah, so for TPUs, Google just launched Jetstream. So Jetstream is an open source, high performance, cost efficient LM inference stack. So Jetstream unifies the serving stack on JAX models as well as PyTorch models while XLA. Jetstream implements the state-of-the-art optimization, including continuous batching, int8 quantization on weights, activations, and KV cache, and more to come, a lot more. So the diagram on the right side shows a simple deployment of Jetstream on GKE. So it has a GKE cluster. It can be a GKE autopilot cluster or standard cluster. The cluster contains 2 node pools. Each node pool is a single host TPU slice. Each node pool hosts one Jetstream deployment. Each Jetstream deployment has one Kubernetes pod. The Kubernetes pod contains 2 containers. One is the Jetstream HTTP server. It receives the HTTP requests and wrap it to the format that Jetstream required and send it over to the Max engine via the gRPC protocol. So the Max engine is a Jetstream inference server. It receives the gRPC requests and performs inferencing. So how does Gemma run on GKE with Jetstream? So based on our internal performance benchmarking tests, when we test run on Gemma 7B with TPUs, we found that it saves up to 3 times reduction in cost per million tokens. Even when we increase the request rate, the throughput per dollar for serving with Jetstream on TPU consistently higher than the baseline inference stack. So we have published all these performance tests and results in blog posts, and we have published our benchmarking tool as well. So you can try it out with your own GKE cluster. So as always, we want to hear your feedback. If you are interested in connecting with a GKE PM or UX researcher, please scan the QR code. Last but not least, Kubernetes is turning 10 this June. Big kudos to the entire community who made this immense success. And many, many thanks to all my teammates in GKE and across Google Cloud and Google to make this happen.